Hello everyone and welcome to this week's plugin tutorial. In this one I'm going to be teaching you all about convolution and kernels, what they are and what you can use them for to create lots of different visual distortions or blurs and things like that. It's going to be a more advanced tutorial. We're going to be using one of the built-in project examples with the After Effects SDK, which will also work for Premiere. This already has some of the code in it, and we're going to take a deep dive onto what exactly everything is. Before we get started with this video, I do want to remind you down below, hit subscribe and the bell icon to be notified of new videos coming out twice weekly on the channel, and down in the description you can check out my GitHub to get coding updates and check out lots of useful code there. Make sure you follow us up there, as well as in the description, follow us on Instagram for other live updates. If you're not already a member of our Discord server, make sure you come and join to get help with scripting, extensions, plugins, UXP plugins, expressions, submit tutorial ideas, hang out with very knowledgeable members, and much more. And if you'd like to help support us on YouTube, you can do so within a link in the description. You can become a member, supporter, premium supporter, or VIP, and this comes with various perks like loyalty badges, weekly tutorials in advance, code in advance, VIP streams, and much more. And also in the description, make sure you check out the link to my various product pages, whether it be AE Scripts, Adobe Exchange, or Gumroad, where I post a lot of free and useful tools that you can check out. Alright, so today we're going to be talking about convolution and kernels, which, if you're not already familiar, what we basically do is we take a matrix of values and we apply it to an image. And instead of just going through all of the pixels in our image, which we usually do with effect plugins, instead of going through and maybe changing all the colors of the pixels based on some algorithm, what this is actually going to allow us to do is create a sort of weighted average and calculate our pixels. So here I have the wiki page for image processing kernels, and this is sort of the idea of what we're going to be doing. Most of the examples here use a 3x3 matrix, and you can think of it like the center point of your matrix is the pixel you're actually looking at, and all of the points around your center point are the pixels around it. So depending on what the value of your center pixel you're currently looking at is, and the values of the ones around it, you're going to create different effects. So in this case, the identity kernel, or the kernel which will give you the exact same appearance of your input image, the input and output will be the same, is to just have 1 in the middle and surrounded by zeros. And it should be noted that some kernels, depending on what kind of programming and setup you use, may have different ranges of values. It may be anywhere from 0 to 1 if they're like a float kernel, or they might be between 0 to 55. It just depends on what exactly you're doing with it, as well as some settings which we'll take a look at in the actual code. So the identity is the same input as the output for your kernel. If we were to basically plug this into the code that After Effects provides for us, this is going to give us the exact same thing that we have as our input image. There are also a few other useful things that you probably are already familiar with that use convolution kernels to create the effects. This can be things like ridge detection. So if you have like a edge detect filter, oftentimes they will use some kind of ridge detection convolution kernel to basically increase the area of the immediate pixels you're looking at, and then as you see around it, actually adding a negative value, which creates this look, but also leaves you with sort of just the edges of your image. Another thing you can do is to do an unsharp mask or sharpening. So what this does is you basically use your center value, increase the number to what you want it to be, the intensity sort of. The surrounding pixels get either 0 or a negative value. And as you can see, you can kind of get an intuitive idea for how these are changing the image. For example, when you have negative values, you sort of get this flat effect in the background, and then when you have positive values, this sort of gives a more punchy effect to ridges and more contrasted areas. But really the best way to use convolution, in my opinion, is to do some kind of blur. Box blurs, Gaussian blurs, most of these use some kind of convolution, because what you're basically doing to create a blur effect, instead of increasing the contrast of all the pixels in your image, you're actually performing a sort of weighted algorithm. In this case, we have an identity box blur, a simple box blur here, which is basically 1/9 for every one of these values. And what it does is it averages all of the values surrounding your focused pixel, and it averages them out. And as you continually average out pixels, you get this sort of blur effect. If you do a more targeted approach again, like the sharpen here, you're going to get more detail. But if you sort of average and flatten everything out to some degree, you are going to get this blur effect. And you can see here, we can get different types of blur effects depending on the arrangement of values. So a box blur is really simple, where you have sort of the same value for every single part of your matrix. A Gaussian blur actually uses a little bit more complicated of an algorithm to create a more rounded appearance. So what you can do to think about this, if these numerical values in your matrix represented, say, the intensity of the pixel in general, you can actually start to create shapes. So this here is a box blur. All the values inside of our matrix are 1. This means that all the weights, all the weighted averages, or any calculations we do is going to be completely the same across the board. And this creates a block, or a box in this case, a 3x3 box. If we do, say, a Gaussian blur, you can see it actually ramps up to a value, then goes back down. And you can imagine this as a sort of gradient box, or even a circle in some cases, which will give you a smoother appearance, especially as you increase the intensity of your blur. A box blur, you'll start to see the box really appear the more you blur it. But a Gaussian blur, because it has this built-in sort of up and down appearance for each of the lines, it actually creates a more gradiented approach, which gets you closer to actually creating a circular bokeh. And the more, basically the larger your matrix is, the larger the average of your pixels is going to be. So if you have, in this case, a 5x5 Gaussian blur, and then you move up to, say, a 50x50 Gaussian blur, or a 51x51 Gaussian blur, which I'll discuss the dimensionality in just a moment, the larger one is going to start to give you a larger appearance of a blur. And sort of, if you were going for a bokeh effect or a blurred lens effect, you would want a larger matrix to do this to. So let's recap. Basically, kernels, which we're going to be doing, applying to our image, allow you to do contrast, reducing contrast, sharpen, unsharp masks, as well as all types of blurs. And we can simply use these matrices to apply these different effects. And the values we give to the matrix inside of it will determine how pixels get averaged or calculated. If it's a high value, it's going to increase sort of the contrast or intensity of our image. If it's a low value or even negative, it's going to sort of remove that contrast, or even remove detail from our image. And in terms of size of the matrix, the larger the matrix size is, the larger the sort of weighted average of this calculation is going to be, which is most obvious in blur effects. If you have a small radius of a blur, you know, your circles or your squares that appear inside of the blur are going to be small. And as you increase the size of the matrix, that's the same thing as increasing the radius of your blur. And for the more advanced users, convolution can actually be optimized quite heavily, to the point where you don't have to necessarily run a horizontal and a vertical convolution at the same time. You can do them separately, and it will be the same amount of time. So if you wanted to create a directional blur horizontally, you could just apply these kernels horizontally to the pixels. But if you wanted to do horizontal and vertical, you don't have to do them at the same time, and you can actually save time by doing them separately, because you can actually multi-thread this type of stuff, especially with GPUs. You can also check out this article to get more into depth, even provide pseudocode, an example algorithm of how you can multiply two matrices together, and also discusses things like edge handling. If you are doing convolution, as you know, many blur effects have a repeat edge pixels option. So oftentimes when you do convolution, there is some edge work you may want to do, whether you extend the edge, you wrap it, you mirror it, you fill it up with whatever. This article is super useful, and it even includes a whole bunch of C++ and all this code. But now we're going to dive straight into the Convolutrix project that comes with the After Effects SDK. This version here is unedited, but we're going to do a few things here to make it easier to understand and see. So inside the render function, this is, I believe, yeah, it's just a render function, no smart render here. We have a check to see if we're in Premiere or After Effects, and this is where we actually run our convolution. We define our convolution kernel up here. And there's some code below to do some other stuff I want to remove. This is to add a blend color, And let me just remove this bit of code here. And I think down to here is fine, actually. May need one more. There we go. So now we just have the sort of convolution code, which is what we want. Let's go ahead and run this and see what our first result is going to be, just to see what the default identity convolution matrix is that this is built into. So the way we're going to be constructing the matrix itself is by using an array. And it seems like in general, the built-in formatting is you want to use an A long as your formatting for your array. So in this case here, we have an array size of 9 created, and then we fill it with some values based on the inputs of our UI, which we will modify. So let's just, I don't know, we can add a clip of anything here, really. Drop into the timeline, and we'll go to Sample Plugins, Convolutrix. Now, I believe this is how it's supposed to look. Yes. So this is a really weird effect, you may think, but this is actually applying the convolution. It's a mouthful. I'm going to go ahead and set a breakpoint right before we apply it. Go to a different frame. And let's take a look at our conv kernel variable. This is our array that is 9 long, and we filled it with some data here based on, it looks like, the sharpen and other inputs from the UI. But if we actually take a look here at the structure, I'll turn this out of hexadecimal display. Let's see what the values are. So we have 0, negative 1 million, 0, negative 1 million. The center pixel is 4 million, and then we mirror the rest. So this is an extreme convolution. And if we were to maybe grab a notepad, if we were to do maybe a visual of this, this is like saying 0, negative 117540, 0, and then 3 is negative 740, 470245. So this is really how our convolution kernel is looking. A lot different than the actual examples we were looking at here. These were all values of like 1, negative 1, 0. So the first thing we're going to do is reduce this to be something more manageable. And specifically, we're going to reduce this to maybe a range between 0 and 255. So the way we're going to do that, we have index number 4. This is the center pixel. Let's go ahead and make this 255. We can remove this kernel sum. And then the rest of our values here, here's what we'll do. In our definition here, we set everything to 0. But what I want to do is set everything to the same value maybe. So let's try everything to be 255. Now I'm going to comment out all the other calculations here and Control-Shift F5 to restart and test this out. I think if I make everything the same value, we can just get a simple box blur up and working. And that's the first thing I'd like to illustrate before we go in and learn how we can create larger convolutions and apply different things. So now, if we go ahead and apply Convolutrix, look at our kernel. Now we have 255 is the first value, 0 for everything else. So what I can do is just say 5, 6, 7, 8, 9. Now all the values should be 255. And if everything is set up correctly, this should give us at least a light or basic box blur. So we'll apply Convolutrix, take a look at our kernel here. All of our values are now 255. Remove the breakpoint and continue. And let's see if we can see a difference. As you can see, we are now getting a very, very slight blur. Now, you might think that increasing the intensity would allow us to change this. So let's first try that. Instead of 255, let's say something arbitrary like 5,000. I know this is beyond the range, but if we want to see how this looks, we can do that. And this isn't necessarily going to increase our blur amount. It might actually make things appear more contrasted, but let's see how it looks. We'll apply Convolutrix. And yeah, as you can see, this makes it extremely bright. And that's because our value is way beyond 255. Even though in this case I'm working in 32 bits per channel, in general, the range for your kernels always needs to be 0 to 255. You can probably get away with some exceptions if you are trying to brighten the image in parts. In fact, I can just remove all of this here. I only want to manually define my kernel in this case. So now I want to take a look at the actual convolve function or method that you are using to apply this kernel to your image. It's very similar to an iterate function where you iterate over all the pixels. So what we have is our world transform suite 1 and the method called convolve. There's also some other useful stuff in here like blend, composite rect, copy, but convolve is quite useful. And if you wanted to go the extra mile, you could even code your own, especially if you're doing GPU work. GPUs are very efficient at doing convolution. But all we have to give it is our in-data effect reference, like any other iterate effect. We give it our input layer. In this case, it's just the layer we've applied to. And then we give it the extent hint, which tells it the height of where it should analyze. And then we have some kernel flags. Some of these flags aren't very well supported, but the default ones are usually what you want to go with. You want a two-dimensional kernel, so it knows that there's horizontal and vertical, and you want to usually tell it to clamp. If you look inside the guide, it says use the first flag to force the values to be clamped into their valid range, and that's determined by the type of item, whether it's an HR, a fixed, or an A-long. And in my opinion, the A-long seems to be the best way to go, and an A-long is 0 to 255 range. Then the next argument is the kernel size. In this particular example, this is defined as a macro in your H file. As you can see, our kernel size is 3. Then you have 4 arguments. You have the R application, the G application, the B application, and the alpha application. If you look at the actual definition here, you have the A kernel, or sorry, it's ARGB, not RGBA. So you have the kernel you're going to apply to the alpha channel, the kernel you're going to apply to the red channel, the kernel you're going to apply to the green channel and blue channel, and then finally you have your destination world, which in this case we're just going to push straight to the output so we can see the result. So you can apply different kernels to different color channels and create a whole wide range of different effects that people probably haven't even thought of too much, because usually you're applying the same kernel to all of your channels to create these effects. Now let's talk about kernel size. After plenty of testing, it's become quite apparent there are a few requirements you want to avoid issues with when dealing with kernels. The first of which is to avoid using even numbers. If you have a kernel size of 4, 6, 8, 10, etc., usually this is going to cause an issue for you. So stick to odd numbered kernels, 3, 5, 7, 9. The higher you go, the actual more stable it seems to be. As soon as you hit 13 by 13 matrix, things seem to be pretty stable. So I'm going to go ahead and let's create a 51 by 51 matrix. So we're going to need to change this from 9 to 51. So I'm going to say 51, but 51 times 51 is the actual size of what we need. So 2601 is the size of this. And if you have it inferred, this array is basically our matrix. It's basically taking a one-dimensional display and converting it to 2D. I'm going to go ahead and empty this, and we're just going to loop through 2601 times. So say int I is equal to 0, I is less than 2601, I++. We're going to say conv kernel index I is equal to 255. Now this is the same thing as we were doing before, but because we have so many indices and numbers to deal with, we're going to use a loop to, instead of having to type out 255 2600 times, that's too much. So we can just use the loop to fill up our convolution, and of course, make sure your kernel size matches the dimension. So if you wanted to make this dynamic, you could have a variable for your dimension, like in this case 51, and then just create an array of that number squared, which in this case is 2601. And then we provide again our dimension here and all of this. Let's go ahead and refresh it. And if you remember, last time we had that 3x3 kernel that we applied to the image, it gave it just a very, very slight blur. This being 51 should give us a much, much stronger blur. It may take a bit longer to process, which is fine. It's a blur. But now, when we go ahead and apply Convolutrix, you can see it's taking a second. You can see we get a much stronger blur. And like I said earlier, as we start to increase these blur values and radii with our convolutions, you start to see the shape the convolution is composed of. In this case, it's a pure, flat, equal value box, and that is becoming quite apparent as you can see these boxes appear. And this is sort of how you define bokeh. The shape of the convolution, whether it's all equal values or whether it gradients towards the center, will all create different shapes of bokeh. And as you can also see, we have some transparent edge because that is how the weighted averaging of convolution works. So that's how you can increase the size of your matrix. And one other tip is you can use a Pascal triangle to get sort of these Gaussian values. As you can see, this kind of matches the values of a Gaussian, oh, sorry, this matches the values of a Gaussian filtered Pascal triangle. A Pascal triangle, if you're not familiar, is basically a way to gather values, and you can use this to create weighted matrices where you basically take a chunk of this and it becomes your matrix. But this furthermore has a Gaussian average applied, it looks like, to it. But this shape will give you a much more rounded natural bokeh shape than in our case right now with this straight box blur where all the values are the same. And again, you can set all this up to be dynamic. So if you wanted to, you could set up a variable to define what the radius is going to be and all that, and then have it auto create whatever kind of kernel or convolution you need. The last thing I think I want to do is I want to maybe link one of the values of the slider. Let's do this convolution amount value to this here. And I'm going to say this value times 2.55, I believe. So because the maximum value of this slider is going to be 100, 100 doesn't get us all the way to our max value of 255. To get there, we need to multiply by 2.55. So what this should now do is give us an error. Let's see. Following is treated as an error. Yes, let's cast this to an A long. There we go. Sometimes you do need to cast your values on if you have a little bit stricter compiling setup. So then now let's go ahead and see if we can link that slider and change the values of our, I guess it would, is it the intensity of the blur or would it end up being the opacity of the image is my question. So we apply this, and I think as we adjust this convolve slider is where we will see the results. So we'll first set it to 100. You can see it's quite blurry. Let's set it to maybe 15. And very, very subtle. Let's maybe turn it up to 50. The image looks to be there still. It's just extremely dark. There we go. So if we link the actual value of the slider to the values inside of our matrix, then it's going to sort of change the intensity of the effect. We probably wanted to keep it at 100 so that we can maintain the same brightness of our image, but also get the blurring effect. But also note that the stronger convolution you apply, it might reduce the overall brightness of your image, meaning that you may want to expand above that 255 range. And I think that's going to do it for this video. I just wanted to go over the basics of what convolution and kernels are and how to use them quite easily in the context of an After Effects or Premiere plugin. It should work for both programs, no problem. And we have a built-in convolve function. Check out Convolutrix. It's the sample included in the effects inside of the SDK. And you can go ahead and link up create a dynamic sized matrix, whatever size you want. Again, a tip is to make sure it's odd numbered because even numbers can cause some weird issues. So create an odd numbered A long based or 0 to 255 based matrix. If you have all the same values across the board, you're going to get something like a box blur. If you sort of increment them like this using a Pascal type triangle, you can get a more nice bokeh Gaussian effect. You could even basically compose letters with this. Like you could create like the letter N, and that then becomes sort of the bokeh convolution that you're doing. And then as you increase the size of your matrix, it's going to create larger effects, whether that's the bokeh or the ridge detection or whatever you're doing. And then you can use the convolve function, which has very simple inputs. You give it a layer, you tell it you want a 2D matrix, and you want to clamp to these 0 to 255 values. You provide the dimension of your matrix, which is whatever the dimension of your matrix is, the square root of that. So the dimension of your matrix is your kernel dimension squared, and vice versa. So there's a way you can dynamically set that up, and then you can apply different kernels if you want to the different channels of your image, or apply the same to all of the channels of your image. So that's going to do it for this video, guys. I hope you enjoyed. If you did, hit the thumbs up button. Down below, hit subscribe and the bell icon to be notified of new videos coming out twice weekly in the channel. And down in the description, you can follow us on GitHub for coding updates, as well as Instagram for other live updates. If you're not already a member of our Discord server, make sure you come and join to get help with scripting, extensions, plugins, UXB plugins, expressions, and much more. And if you'd like to help support us on YouTube and become a member, supporter, premium supporter, or VIP, which comes with cool perks, you can do so in the link in the description. And also down there, you can check out the links to my various pages, whether it be AE Scripts, Adobe Exchange, or Gumroad, where you can check out some free and paid tools to help you out. Thanks again for watching, everyone. We'll see you next time.